So Renato will speak about algebraic and geometric classification of non-associative algebras. Please.
Thank you. Can you hear me? It's okay?
Yes, yeah.
Okay.
It's okay.
First, I'd like to thank the organizers for this opportunity. So I will talk about two works. The first is the algebraic and geometric classification of Zinbiel algebras. And the second is the algebraic and geometric classification of antiassociative algebras. The first is a joint work with Professor Ivan Kaygorodov and Professor María Alvarez. And the second is a joint work with Professor Ivan Kaygorodov and Crislaine Kuster. Okay. In the first part of this presentation, I will talk about some results about Zinbiel and antiassociative algebras, and some known results about classification of algebras. So in the second part, I'll talk about the algebraic classification. And in this part, I will talk about the case of Zinbiel algebras. And since the method is similar, so I will just present the results of antiassociative algebras. And in the third part, I will talk about the geometric classification. Okay. A Zinbiel algebra, or left Zinbiel algebra, is an algebra that satisfies this identity. These algebras were introduced by Lodey in this paper. Under the Koszul duality, the operator of Zinbiel algebras is dual to the operator of Leibniz algebras. In this paper of Aguiar, it was proven that a Zinbiel algebra is equivalent to a commutative then uniform algebra. Zinbiel algebras also plays an important role in the definition of Preges-de-Haber algebras. The variety of Zinbiel algebras is a proper subvariety in the variety of right commutative algebras. A Zinbiel algebra with the commutator multiplication gives a Torticara algebra. There is also I study in Rec cohomology that the Zinbiel algebras appear. This is a recent work. They also appear in a construction of a Cartesian differential category. Zinbiel algebras also appear in this paper that relates with number theory. And in this paper by Lodey, the three Zinbiel algebras were shown to be precisely the shuffle product algebra. In characteristic 0, any proper subvariety of a variety of Zinbiel algebras is nilpotent. And Zinbiel algebras are also pre-commutative. That is, if you consider a new product, this new product here, will obtain an associative commutative algebra. And there are also interesting results about Zinbiel algebras. In this paper, the hypothesis of Zinbiel algebras, it was proved that this algebra, when you define this product, is a Zinbiel algebra. For example, if K is an algebraic closed field of positive characteristic, then every finite Zinbiel algebra is solvable. And also in this context, it's possible to show that every Zinbiel new algebra is nilpotent. Okay, and of course there are much more results, but this is just some few results here about Zinbiel algebras. So let me say something about antiassociative algebras. An antiassociative algebra is an algebra that satisfies this identity. Okay. These algebras are a particular case of Lie-type algebras that are defined by this kind of identity. And these algebras were considered in this paper. They are also a particular case of alpha, beta, gamma algebras, and also particular case of extended Lie-type algebras. Okay. There is a relation with CB algebras that are algebras that satisfy this condition. And in particular, an anticommutative algebra is a CB algebra if and only if it's a antiassociative algebra. Okay. There is a result by Garcia and Martinez and van der Linden that proved that an algebraically coherent variety of anticommutative algebras is either a variety of Lie algebras or a variety of antiassociative algebras. Okay. Antiassociative algebras are also related with anticommutative de alternative algebra. And if you consider antiassociative algebra, and if you take the algebra A+, we'll obtain a mock Lie algebra. Okay. That is a Jordan algebra of Lie index 3. And also a dual mock Lie algebra is an anticommutative, antiassociative algebra. And all these results appear in this paper, especially exceptional mock Lie algebras. Okay. Also, in this paper, the non-cosinus of the corresponding operator for antiassociative algebra is proven. And also, antiassociative algebra appear in gauge theory. So you can see this in this paper by Ancon. And of course, there are other results and papers that antiassociative algebras appear. Okay, now let us talk about some known results about algebraic and geometric classification of algebras. And here again, I will just talk about some few recent papers. Okay, the first is about the classification of n-dimensional non-Lie Malsev algebras. This is about the algebraic classification. And here they classified the non-Lie Malsev algebra with n-4 dimensional annihilator. And this paper is interesting because they write all the steps with many details, so it's a good source to read about algebraic classification. In this paper by de Graaf, it was done the classification, algebraic classification of 6-dimensional nilpotent Lie algebra. Here with some restriction about the field. And some years later, it was done the full classification over an arbitrary field, the algebraic classification of 6-dimensional nilpotent Lie algebras. Okay. In this paper by María Alvarez, it was on the geometric classification of 8-dimensional 2-step nilpotent Lie algebras. In this other paper, this recent paper, it was done the algebraic and geometric classification of 4-dimensional complex nilpotent terminal algebras. In this other paper, it was under the classification, geometric classification of 3-dimensional nilpotent algebras, 4-dimensional nilpotent commutative algebras, and 5-dimensional nilpotent anticommutative algebra over C. There is also the algebraic classification of 5-dimensional nilpotent Jordan algebras. And in this paper by de Graaf, it was classified it was an algebraic classification of nilpotent antiassociative, nilpotent associative algebras of dimension up to 4. Here over any field. And another result is the geometric classification of Jordan algebras of dimension 4. And okay, these are just few examples of results about classification of finite dimensional algebras. So now I will start explaining the method to obtain the algebraic classification of Zinbiel algebras. And as I said, since the method is similar to the case of antiassociative algebras, I will only present the classification theorem in the final. Okay, we consider A Zinbiel algebra over C, and via vector spacer also over C. The first part, let us define the second cohomology group, A2. First, we consider the space Z2 of cocycles that is the set of all bilinear maps that satisfy this identity that's related with the identity of the Zinbiel algebra. And if you consider a map F from A to B, we can define delta F by this identity, by this equality. And we can define the set B2 by this kind of elements. So the second cohomology group is just the quotient group of Z2 by B2. Here we also consider the action of automorphism group. So we take an element phi in the automorphism group of the algebra of Zinbiel algebra A. We can define this action on Z2 by this equality. We can prove that the B2 is invariant under this action of the automorphism group. And with this, you can induce the action of the automorphism on the second cohomology group. Okay. Now consider a Zinbiel algebra A of dimension M over C. V will be a vector space over C of dimension K, and theta is a bilinear map. So here we define a linear space, A theta, by defining this product, this new product, given by this identity, where xy here is the old product. And we call the algebra A theta a k-dimensional central extension of the algebra A by the vector space B. And we can prove that this new algebra A theta is a Zinbiel algebra if and only if the bilinear map is an element in Z2. Okay. Here are some definitions. We have the definition, the standard definition of the annihilator of the algebra A. Here we have the annihilator of the bilinear map theta, and we have this relation between the annihilator of A theta with the annihilator of theta and the annihilator of A. Okay. And here we have this important result that say that if you consider that every algebra with a non-zero annihilator is a central extension of a smaller dimensional algebra. So this is the reason that usually in this paper by of classification of algebras, nilpotent algebras are considered. But here, in our case, Zinbiel algebras, and also in the case of antiassociative algebras, they are nilpotent. So we have this result, okay? One more definition. If you consider an algebra A and I a subspace of the annihilator of this algebra, then we call this subspace I an annihilator component. And here we say that a central extension of an algebra A without annihilator component is called a non-split central extension. And in this work, we are looking for central extensions of Zinbiel algebras and antiassociative algebras that are non-split central extension. So with this objective in mind, we need to think about the problem, the following problem. If you have two central extensions, we need to check if they are isomorphic or not. So to solve this problem, we'll need to consider the action of the automorphism group. Okay, and here we also need to verify or try to avoid the central extensions that are split central extensions. So for this, we'll consider a basis of the space V, and theta, an element here in Z2. This element can be written in this way, where this theta I are elements here. So we have this equality about the annihilators. Theta is in B2 if and only if the theta I are in B2. So given a central extension, A theta, if you consider this element written in this way, and if you suppose that this intersection is 0, so A theta has an annihilator component if and only if these elements are linear dependent in A2. So we have a criterion to avoid the central extensions that has an annihilator component. Now we consider V as before, a finite dimensional vector space over C. We consider the Grassmannian GK of this space V. We consider the Grassmannian of A2, And we can define an action of automorphism group of the on this Grassmannian. And here we just take an automorphism phi. We can write an element of the Grassmannian in this way. So the action is just consider the phi applied in each of these elements and consider the class of them. Okay. If you have two elements in this Grassmannian, and if you write these elements in this way, we have that these two elements are equal. Then we have this equality of annihilators. So with this, we can introduce this set, the TS, that is a set of elements in the Grassmannian, that this intersection of annihilators is 0. And this set has the property that it is stable under the action of the automorphism group. Okay. Using this set TS, we'll define this new set E as the set of all non-split S-dimensional central extension of A by this linear space V, this S-dimensional linear space. And we can write the set in this way. And finally, we have that these two central extensions are isomorphic if and only if the orbit, these two orbits are the same. So with this correspondence, we can now describe exactly the method that we use to classify, to obtain the algebraic classification of these algebras. So if A prime is a n minus s dimensional Zinbiel algebra, so the following procedure will construct all non-split central extensions of A prime. The first step will determine A2, the annihilator and automorphism group of this algebra of dimension n minus s. We determine the set of automorphism orbits on TS, and with these orbits, we can construct the Zinbiel algebras associated with a representative of each of these algebras. Okay. To do this, we consider the following notation. We always write a basis using these elements, and we write delta ij as this bilinear form. The set of special bilinear forms forms a base of the space of bilinear forms. And since to classify for example, in this case, the 5-dimensional Zinbiel algebras, that is our objective in this first part. Since there are a lot of computations to be done, I will explicitly here one example. So in this example, I will consider this two-step nilpotent 4-dimensional Zinbiel algebra, R2. The elements E1, E2, E3, and 4 is a base of this algebra. And here, I will put just the non-zero products. Okay, so these products define the Zinbiel algebra. The second cohomology group of this algebra is generated by these elements. To make the computations, we use the following notation. Okay, just to avoid the sums that appear. And following the method, we consider an element in A2. So it can be written this way. The automorphism group of this algebra is generated by these two kinds of matrices. Okay. And the action of this automorphism group using, for example, the first kind of automorphism can be written by this equality, and computing these elements will obtain they here. So the objective here is to make a choice of this automorphism to obtain all the orbits but first we need to look to see what happened with the annihilator. Since it is generated by these two elements, in this classification, we cannot have this product 0. So we consider this element equals to 1, alpha 4 equals to 1. And here, if you choose X, Y, T, and U in the automorphism, if you make this choice and the other entrance equal to 0, we will obtain only one representative that is generated by this element 3 plus 4. Okay, and when you return here to see what these elements are, in the case it is the sum is and this other element, we can we obtain the following algebra that we denote by Z5. It's just the order that we classified, and it's given by this product. And remember that the products that do not appear, they are 0. Okay. Therefore, we have this theorem that gives to us the algebraic classification. So in this case, the 5-dimensional split non-two-step nilpotent Zinbiel algebras can be described by 6 one-parameter families and 53 additional isomorphism classes of algebras. Okay, the list is so huge, so I do not include it here. Okay. And in the case of antiassociative algebras, the steps to classify are similar. And the result is that the complex 5-dimensional non-two-step nilpotent antiassociative algebras can be described by 4 one-parameter families and 26 additional isomorphism classes. Okay, and this is the first part of that is the algebraic classification. Now let me talk about the geometric classification. So we continue considering V an n-dimensional vector space. This space home has a structure of a fine variety, CN3. We fix a basis of this vector space V, and n element in this home is determined by n3 structure constant that we denoteCijk in C. And we say that a subset in home is Zarisk closed if can be defined by a set of polynomial equations in these variablesCijk. Okay. So let's see a set of polynomial identities. The set LT will be the set of algebra structures on this vector space V that satisfy the identities from T, and the sets form a Zarisk closed subset of this variety. We have an action of the general linear group GL on the set LT given in this way. So LT can be decomposed into GL orbits that correspond to isomorphism class of algebras. So we denote an orbit of an element in this way, and its Zarisk closure with a bar on this orbit. Okay, if you consider two algebras, n-dimensional algebras that satisfies the identities from the set T, we'll denote mi and lambda, the elements in LT that represent these algebras. And we say that the algebra A degenerates to B if we can, and if lambda is in the Zarisk closure of the orbit of the lambda is in this Zarisk closure, okay? And if it's not in this Zarisk closure, we say that the algebra A does not degenerates to B. Okay. Here we also are interested in to find rigid algebras. So we say that A is rigid in this set LT if this orbit is an open subset, a maximal irreducible closed subset of a variety is an irreducible component. We call it an irreducible component. And it's known that if in an algebra, the algebra A is rigid in the set, if and only if this closure is an irreducible component of LT. Okay, so to obtain this irreducible components and this and also, of course, the rigid algebras, we'll check for all these algebras obtained in the algebraic classification, if they degenerate or not to the other algebras. So here we have an important result that we use to this classification. That is, if an algebra degenerates to another, here an algebra A degenerates to B, and they are not isomorphic, then the dimensional of the derivation of these algebras satisfies this inequality. So to compute, to check if an algebra A degenerates to B, we only check this assertion in the cases that the dimension of derivation satisfies this inequality. There are other relations that can be used. For example, about the annihilator, but here we mainly use this relation about the derivation of these algebras. An example, we consider these three algebras that were obtained in the algebraic classification, and here are the product that define these algebras, 5-dimensional Zinbiel algebras. And if you compute the dimension of the derivation of these algebras, we obtain that for Z9 the dimension is 6, and to the other algebras the dimension is 7. So we know that Z6 does not degenerate to Z1. Okay. And to this case, since it satisfied this relation of the dimension of derivations, it's possible to check if Z9 degenerates to Z6. So we'll see this in the next example. Okay. Of course, this is an easy case to say that an algebra does not degenerate. In other cases, it's much more complicated to check if an algebra does not degenerate. Okay, this is just a simple case. Okay, so let us say how we can check if an algebra degenerates to another. So we consider A and B, two algebras represented by mu and lambda in LT. E1 to En is a base of B, and Cijk will be the structure constants of lambda in this basis. So to check if A degenerates to B, we need to construct elements Aij, elements in T in the complex numbers, such that when you consider these bases that we call a parameterized basis, the structure constant in this base, when you make T the limit of T going to 0, we will obtain that the Cijk0 is exactly the constant structures of the representative lambda. Okay. An example to see how it works. Here, of course, in a simple example, we consider these two algebras, Z6 and Z9, and you check that Z9 degenerates to Z6. If you consider this degeneration basis, if you make all the products here, I will just show the non-zero products. Note that this first 4 products will obtain exactly the product of algebra Z6. And here there is one last product that when you consider the limit of T going to 0, this product will be 0. So we obtain exactly the algebra Z6, and this proves that Z9 degenerates to Z6. Before presenting the geometric classification theorem, there is an important remark to say here. In this geometric classification, we obtain the classification of, for example, in the case of Leibniz algebra, we obtain the classification of all 5-dimensional Zinbiel algebras. Because we have this result, that's the geometric classification of 2-step nilpotent algebras and applications, that proves that classify the geometric classification of 2-step nilpotent algebras, even if that is it's not completed the classification of 2-step, the algebraic classification of 2-step nilpotent algebras. Okay. So in the case of Zinbiel algebras, we have that this variety has dimension 24, and it has 16 irreducible components, And in the case of antiassociative algebras, it has also dimension 24 and 8 irreducible components. Okay. Thank you.
Thank you, Renato. Are there any questions, remarks, comments? Let me see in the chat. Okay, so I don't see any questions. So let's thank Renato again.